And then there were also three other people, Lucas, Joshua, and Nicole, who worked on the paper with us, but were not able to present. So quick shout out to them. If you haven't figured it out by now, we are Team 3. We came up with the mission Polemos-1 for the Mars Society's International Mission to Mars design contest. And I suppose I'll hand it over to you, Peyton, for our introduction.
I don't need this microphone. That's all right. Team North America West presents Polemos-1, a 550-day, 28.5-ton mission for Mars, focused on creating a foundation for similar missions and the technology that drives them. Since the planet Mars is named after the Roman god of war, we chose to name our mission Polemos-1 after the divine personification of war in Greek mythology, Polemos. By the time the mission's two possible launch windows open in 2031 and 2033, the equipment we bring on the mission will have matured and solidified into a support structure and jumping off point for not only our pioneering first 5, but for exploration of Mars as a whole.
Polemos-1 will be landing in Milankovitch, a crater 118 kilometers in diameter, located in Arcadia Planitia. We chose this location because it's one of 8 sites in the Martian mid-latitudes where ice has been found especially close to the surface and in very large amounts in scarps in the southwest region of the crater. The presence of large amounts of subsurface ice in Milankovitch is very important for Polemos-1 because, well, it's required for the astronauts to have food. Additionally, future Mars missions are likely to need to produce fuel for their return using resources on the surface. Water ice will be one of those resources, and Polemos-1 will be able to help out those future missions by taking photographs of the landing site and mapping where the water is in Milankovitch. Now, as you've probably figured out, the image on the left is an infrared image of the crater. On the right, we have the scarps in question and a red X marking where the ideal landing site would be. All right, we're going to move on to the next slide now, but that involves Maximus. Can you take this
Can you
away?
hear me? Can you hear me?
We can hear you. We can't quite see you. Okay. Yeah, take it away.
The ideal Mars habitat must protect the health and safety of the crew while sustaining productivity. Factors include life support systems, radiation protection, ease of both inter-vehicle activity and extra-vehicle activity, habitat space, cost, and more. Domes are a staple of Mars imagery, but are impractical. They are difficult to build, not space efficient, nor do they offer any radiation protection. Underground habitats were proposed by engineers in the 1990s, but were also found to be impractical, requiring more equipment and time than any other proposed habitat design. For Polemos-1, our team proposes a custom habitat design to fit the criteria of the mission. Taking design cues from the NASA Habitat Demonstration Unit and other Mars habitat designs to keep costs low, our team proposes adding a water tank to the top of the hab in order to protect against radiation. Amenities include a hygiene module, geolab, medical station, maintenance workstation, and robotics workstation. The habitat will come pre-assembled, weighing approximately 16 tons. And you can see in the slide here, there's an image of what the hab kind of concept would be with the water tank.
For spacesuits, astronauts on the Polemos 1 mission will use a modified version of the experimental Z-series spacesuit developed by NASA. The suit will be made out of a nylon tricot, Kevlar, and Nomex blend, with the gloves using spandex for extra flexibility. The Kevlar and Nomex will keep the suits durable and sustainable for the entire Mars mission. The spandex on the glove portion of the suit will be needed for flexibility when setting up the hab or performing scientific tasks. In addition, the helmets will have a thin sheet of gold on them, giving astronauts protection from the sun's UV radiation when they're outside of the hab or rover. The calculated weight of the spacesuit design is approximately 13.5 kilograms. In addition, the life support system and oxygen needed for an EVA weighs 22.5 kilograms. This comes to a total weight of about 36 kilograms, making maneuvering easy. The suits will have an integrated hatch, what we call a suit port, on their backpacks, allowing the astronauts to seal their suits to a docking port and enter the habitat or pressurized rover. This system prevents contamination and minimizes the amount of Martian dust crew members are exposed to, since the exterior of the suit and the dust carried on it will never enter a pressurized area. Sebastian?
The EVA suits you just heard about will be excellent for exploring a small area near the landing site, but during their stay on the surface, we expect that the astronauts will need to explore other areas of the crater, and those could be more than 100 kilometers away, which isn't exactly walking distance. To do so, they will need a pressurized rover, like the one in the image on the right, which is an artist's concept of the rovers for NASA's austere missions to Mars plan. The rover for Polemos 1 will be very similar in shape and size, even though the rest of our missions are very different. Astronauts will be able to attach the suit ports you heard about to several hatches on the rear of the vehicle to enter and exit the pressurized cabin. This will be able to house 2 of them for up to 3 weeks, or all 5 members of the crew for 1 week in an emergency. That should leave them more than enough time to travel to the other edge of the crater and back, since the rover has a top speed of a blistering 20 kilometers per hour. The range of the rover is really only limited by the amount of time the life support system can support the crew for. That is about 3 weeks for 2 astronauts, because eventually the rover will need to return to refill the oxygen tanks and stock up on food and other consumables. The rover's power source is a scaled-up version of NASA's Advanced Stirling Radioisotope Generator, which will produce 5 kilowatts of electricity. This RTG will produce electricity constantly, so the rover won't need to stop to recharge or to be refueled, which is why its range is essentially unlimited. Unlike a solar-powered rover, this rover will still work during a dust storm. The rover's scientific capabilities will be limited to weather sensors, visible light and infrared cameras, and a ground-penetrating radar system. This will be used to map subsurface features, including the ice deposits Polemos 1 will land nearby. Most of the data gathered during a rover expedition will be collected by astronauts on EVAs, though, using cameras, shovels, and core sampling drills to collect samples for analysis at the hab. These samples will be transported back in containers on the outside of the rover so that the astronauts won't accidentally contaminate them.
Massive water mining and fuel production plants like Mithril, which I'll touch on later, have been discussed as great ways to fuel and feed an equally mammoth Mars colony. However, operations like that are currently too far off and will probably require an entire mission's time to set up. For Polemos 1, we will use Honeybee Robotics' red water a system with scale models already tried and true in thermal vacuum chambers set in a Mars-like environment. The drill uses a combination of traditional drilling with an auger, coiled tubing or CT drilling already used for industrial oil drilling on Earth, and a special strategy called the Rodriguez well for melting ice and cycling it through a heat source. This creates an efficient positive feedback loop that uses minimal energy to collect from a well of ever-growing subsurface ice water. It requires no special source of electricity and doesn't even need a heater for the water, since that can be run through a nearby kilopower reactor. The two diagrams here show the steps of well formation and water extraction, as well as the internal components of the drill.
The life support system of the crew habitat will be pressurized to 101.3 kilopascal and or 14.69 psi. The habitat atmosphere will be 80% nitrogen and 20% oxygen. The air recycling system must remove the CO2 and supply 1,700 pounds of new oxygen per day, or the total of 617.3 tons of oxygen per year. The humidity will be kept between 20 to 40%, and the temperature is kept around 21 degrees Celsius. Daily, humans use 100 watts of power, so the life support system of a settlement, which includes food production, will require approximately 10,000 watts to 20,000 watts of average power per inhabitant. One person will intake 0.8 kilograms of oxygen, 1.8 kilograms of food, 2.5 kilograms of water, and will give out 1.4 kilograms of CO2 and 0.96 kilograms of H2O gas and 1 kilogram of waste and 2 kilograms of H2O liquid. The CO2 treatment will give out oxygen and methane, and we can reuse the oxygen into the habitat. The waste treatment will separate solid and liquid waste. And you can see this chart, which gives in detail on how the life support system is going to work. And now Maximus can take it over.
How are we going to power an extraterrestrial habitat? The design must be lightweight, safe, and power efficient. NASA estimates that a Mars base will need 20 kilowatts of power. Options include solar panels, or radioisotope thermoelectric generator, or RTG, and kilopower reactors. Solar panels are seen as a quick and dirty solution, but have many downfalls. The efficiency of the solar panels will be 20% due to dust storms, distance from the sun, and diurnal oscillation in solar flux. A large solar farm would have to be built, increasing cost, complexity, and weight. RTG reactors are a type of nuclear battery used in most unmanned space missions. However, they aren't viable for a power source due to limited power output. Kilopower reactors are a type of nuclear reactor created by NASA for use on the Moon and Mars. The Kilopower Initiative started in 2015, led by NASA and the DOE's National Nuclear Security Administration. Kilopower reactors can generate 10 kilowatts continuously for 12 to 15 years and are small, making them cost efficient. Heat generated from the kilopower reactors will be used to melt ice and supply the base with water. Polamos 1 will use 2 kilopower reactors with a combined power output of 20 kilowatts, an estimated weight of 3.3 tons. And here on the slide, you can see what an artist's impression of a kilopower reactor on the Moon and Mars.
All right, we're going to go back into, wait, hang on. One of you guys did this. Which one is it? Oh.
You did. I'm really sorry.
Oh, no worries. It's the
Not
new
sure if
normal.
I'm not sure if it's when we bring your other friend in. The James is specifically asking to make sure that this would happen.
Oh, thank you.
Yes.
We need a please hold for technical difficulties card or something.
Max, you can unmute yourself. Obviously, none of this should be happening, right? All right, I think you're good. Don't stop sharing it.
Okay. Thank you, Maximus. Getting back to yes. Awesome. Getting back to the presentation. As you know, Polaris 1 is meant to build a foundation for future missions to Mars by testing technologies, but it will also study Martian geology, the history of the Martian climate, and even the possibility of life on Mars, past and present. Thanks to their advanced equipment and diverse skill set, the crew will be able to study these topics in far more detail and with far more accuracy than a robotic mission ever could. Assuming the crew can't use the rover to find a way out of the crater, which isn't in the mission plan, but could happen, they will have roughly 11,000 square kilometers of Martian soil to explore. There's no way they can thoroughly investigate all of that land. And it's back. Okay. Really quickly before it breaks again. They're going to have to concentrate their exploration on the 6 areas we've tried to label in red in the top image and spend 2 to 3 months, as you can see in this draft schedule, on each of those areas, rather than exploring every square centimeter of the crater. The astronauts will begin by exploring the scarps near the HAB, using a combination of EVAs and rover trips. Ground-penetrating radar will be heavily used to map the ice inside the scarps. After water has been found and the red water drilling rig is operational, the astronauts will explore areas of the crater that are further away. For these longer trips, the rover will be crewed by 1 astronaut with science training and 1 capable of repairing the rover in an emergency, since they'll be going outside of walk-back distance. Astronauts on EVAs won't be able to carry many tools, and the rover lacks the space for all of the equipment necessary to fully analyze samples, so those will instead be brought back to the HAB. The other 2 astronauts will be able to use spectrometers to study the composition of rock samples and compact color biofinders and a signs of life detector to search them for biosignatures. Additionally, water melted from samples of the ice in the scarps will be filtered through an agnostic life finder to search for molecules similar to DNA, and another ALF will be attached to the red water drilling rig you heard about to filter the water it collects before use. Astronauts should also be able to study the history of the Martian climate by analyzing ice cores for trapped gases, like scientists do in Antarctica already. As you can see on this draft schedule, the last month of the mission will be dedicated to sorting through the samples that will be collected and choosing which ones to take back to Earth. For the competition, we were only told there would be a Mars ascent vehicle available for our crew, but we didn't know how much space there would be to bring back Mars rocks. We assumed there would be some, though. Nish?
Every astronaut will wear 2 bracelets at all time, a personal active dosimeter and a physical fitness monitor similar to a smartwatch. First, the Palmos personal active dosimeter, or PPAD, is a smaller second-generation version of the European crew personal active dosimeter installed on the ISS in 2016. And it'll both measure the amount of radiation the astronauts are exposed to throughout the mission and provide the astronauts with real-time data about their exposure. The physical fitness monitor will track the heart rate, blood pressure, and quality of sleep of every astronaut. In addition to the radiation exposure, the astronauts are likely to lose muscle mass, especially their anti-gravity muscles like quadriceps and back muscles. During their stay on Mars, which will be measured by a bioelectric impedance analysis system, since this is a simple and quick process. BIA testing will also be performed about once every 3 weeks. This regular testing will mean that all astronauts can be tested at the same time. Every time 2 crew members return to the habitat from a rover expedition, giving doctors data for all the astronauts at the same time.
All right, it's time to improvise a shorter path through this slide. Yes. One of the technologies that Polemos will be bringing along to Mars is a spider-like rover named Alala, after the Greek spirit of the war cry. She is a scaled down to 1/4 model of the athlete system, developed initially for the moon by initially developed for the moon, and it's planned that we'll take it to Mars with a concept mission by the University of Illinois called Mithril. The main point of the athlete operational shakedown is to test Alala's decision-making skills with her autonomous navigation suite and her driver-in-the-loop step placement skills, which will require an operator to go along on the mission. And to develop a manual of real-life fixes and possible failure modes, Alala will be brought along on the pressurized rover while the astronauts are on their expeditions.
The agricultural system we chose for Palmos 1 mission is hydroponics, as it is an efficient and relatively under-demanding option for Martian astronauts. The system utilizes water sourced from Martian ice, as well as micronutrients such as nitrogen, phosphorus, and potassium to create a nutrition solution that produces a wide variety of traditional produce. This allows Martian astronauts to avoid reliance on soil for plants' nutrition, which is not the most efficient or beneficial option, as hydroponic produces plants 50% faster and converts 10 times the amount of water. Due to the hydroponic system being located indoors to protect against radiation, botanical grow lights will be utilized as the plant's energy source. The hydroponic grow lights will produce a magenta light frequency as it combines benefits of both red and blue light. Red light is being shown to be beneficial in producing taller and leafier plants, while the blue light promotes leaf expansion, sprouting, and root development, which are all important factors in the quality and efficiency of plant growth. In addition, benefits of a hydroponic system is that it requires minimal maintenance, especially when compared to other options such as aeroponics and traditional farming methods. Maintenance includes draining and refilling the hydroponic nutrition solution about twice a month, as well as simple cleaning measures to ensure the system stays in its proper condition. The image to the right depicts an active indoor hydroponic system similar to the one being used for the Palmos 1 mission. These are our general statistics, and thank you for all your attention. If you have any questions, you may let us know now.
I would probably plan out more like the different components we needed, because we had the rover, we had the hab, we had all that. But the red water drilling rig was put in a week before the thing was due. We forgot we needed a water source, and I just did like 3 days of running through like CT drilling white papers trying to find a good drill for us. So I'd plan that out better.
Just to add on to that, I think documenting our research a little bit more would have helped in the creation of this presentation. There were 3 people who worked on parts of this who couldn't be here. So we had to go through the paper and figure out what they did because we didn't work on some of the parts that we had to talk about.
And I would say that we were editing the slides till the end because we had a lot of information on the slides. So one thing we should have improved was to put less information on slide and make it more basically interesting with more pictures and important facts, but tell out all these statistics and present it that way.
I think we had the right idea the first time we did the slides, because in the actual presentation, it was only pictures. We had no time to write text. So we just put a bunch of pictures on the screen and explained what they were. And it actually went a lot faster than this one did and was probably easier. Bye, Max.
Hello? Oh, it's working now. So, hello everyone. We are Team 1 from the Mission to Mars Design Class and Competition. Our design is called Valles Marineris Exploration Mission. And here's us. I'm Antoni. I am the team leader. Claudia, she was doing mainly science. Emilia, she was doing mainly engineering. Leo, he was doing energy management and crew selection. And Rachel, she is unfortunately not with us right here. She was doing mainly life support. And our mentor, Tobias, he's right here. So firstly, a quick mission overview. The primary goal of the mission is maximizing the science output. Really, when you are on Mars, you don't want to waste any time. So just doing as much science as possible. We had a 30-ton weight limit imposed on us by the competition. So we will be using ISRU extensively. We will be landing a cargo mission 2 years prior to the arrival of the astronauts. This will give us enough time to produce all resources such as water, propellant, food, and other consumables up front. We were allowed to use upcoming technologies, and by upcoming, I mean ready by 2030. So we made sure to take advantage of that. And this is partly why our proposal is so radically different from the current ones, such as Mars Direct, because in real life, space missions use hardware and technology from 10 to 20 years ago, and we're using technology 10 years ahead. We will be taking 6 astronauts with us. They will be staying on the surface of Mars for 18 months. These are all the maximum allowed amounts by the competition. And while we think that the time limit is reasonable, if we had the possibility, we would have taken more astronauts with us. So now Claudia will tell you more about the landing site and the science of our mission.
So our main base is located in Candor Chasma, the northern branch of the very center of Valles Marineris. It's 8.5 kilometers deep basin between 600 and 800 kilometers in diameter. Its variety of differently characterized branches is enclosed mostly by steep cliffs. And here is our landing site. It is placed near Martian equator, which ensures optimal sunlight exposure throughout the year. And because of its depth, Candor Chasma has a unique microclimate. And this is the only known place on Mars where fog can exist. And such a high air humidity could be a great source of water. And speaking of water, the European Space Agency ExoMars orbiter discovered that about 40% of Candor Chasma's regolith contains chemically bound water. It exists in form of sulfates and hematites, which deposits are already mapped across multiple places in our landing site. But Candor Chasma is more than a rich source of mineable materials. Its location in the deepest rift on the planet ensures that we can discover the geological map of the history of Mars. The cliffs of different slopes allow us to study the geology, but also let us better understand the current state of the Martian climate. In other words, its place filled with water, resources, climatic riddles, and unique structures, all of them being a key to understand the red planet. We can roughly divide our scientific goals into 3 somewhat intervening groups. First, understanding the history of Mars. Second, understanding current Mars. And third, understanding what can be done to make Mars our home. We start with water. We are going to take advantage of the high abundance of chemically bound water exists in the regolith near our base. Rich sources of sulfates and hematites will serve us also as building resources, both directly and as a materials for production polymers for 3D printing. A study of the chemical composition can also serve us as tracer of the history of the Martian climate. And since some of chemical components tend to form in seas of given properties, we could use them as tracer of the past microshell life. The curious microclimate of various marine areas is worth studying on its own. The already mentioned water fogs can be another source of water. We should also investigate the geological formation, such as recurring slope linea, which may be connected with water. Which may be connected with seasonal water activity. The places we plan visit with our EVA mission and drones are home to unique formations. We will focus on analyzing the geological cross-section available on the cliff tips. This will be an invaluable window on the Martian geological past. We'll analyze the alluvial and sedimentary materials to study the volcanic activity. The study of the weathering of rocks and analysis of such structures like yardanks should tell us about the composition of the Valles Marineris bedrock and thus the history of its formation. But there is another side of our mission. We must also focus on the human part of our study. We will learn how to thrive in Martian environment, how to make the base optimally useful, efficient, but also cozy. But study of human behavior is an important aim, but providing for astronauts and keeping them healthy is likewise the crucial point. Because of that, we will study how to fertilize the Martian soil using local resources, I mean sulfates, how to grow a variety of food, keep fishes, and how to keep safe in ever-changing seasonal variation on Mars. We are aware our goals are ambitious. Therefore, we must prepare ourselves by designing the best laboratory space possible. The well-equipped multifunctional lab will be divided into specialization section to ensure safety of our crew. Our equipment will be, for example, fume vents, radiation chamber, sterile chamber, airtight chamber, and there are only a few precautions we take to make the state of science and prevent any contamination. A spacious common area in the lab will serve also as a place where crew will be spending much time together. And after all, here in the lab, they must feel comfortable. And yes. And now Leo will tell something about energy supply.
All right, thank you, Claudia. Now for the energy supply in our mission. The energy supply is based on solar power and chemical storage. We will utilize about 200 kilowatts of ultralight plastic solar panels that will be automatically deployed after the spaceship lands. The power to weight ratio will be about 0.4 kilowatts to a kilogram. Now, an additional 100 kilowatts can be produced by modular high temperature fuel cells with 80% efficiency. Utilizing the solid oxide fuel cell technology. Batteries are used only to guarantee interruption-free power supply and a central backup. Mobile devices utilize the same batteries that are interchangeable to save weight. The methane will be produced by the same fuel cells in reverse mode when surplus solar power is available. The main energy storage will be an inflatable plastic tank for methane to produce power at night or during prolonged sandstorms. The vehicles utilize the same fuel cells as the fuel cells at the base camp, this way providing a high degree of interchangeability and weight reduction. Now, for the in situ resource utilization, we plan to utilize the resources from mass for production of all essential consumables. Water collected and CO2 from the atmosphere are fed into the same fuel cells we use for power production, but in reverse mode. We generate syngas that is the base for further products. Methane as fuel, oxygen for burning or breathing, basic plastics to produce material for 3D printing. This is due to the unparalleled efficiency of high temperature fuel cells in reverse mode. It allows us to produce large amounts of fuel to increase supply security, as well as further reduce the emission weight by utilizing the same fuel cells for power generation and chemical production. Now, the target for our food production is to have the most lightweight solution that will keep our astronauts healthy and alive. So we decided to use an algae bioreactor with 3 different kinds of algae to provide 3 key nutrients: carbohydrates, proteins, and fats. This will cover about 90% of the required calorie intake. The algae are dried, processed into soylents, and then mixed with vitamins and flavors so that the astronauts won't get too bored of the food. The remaining 10% of the diet consists of meals that we take from Earth to add variety and boost morale. We will also use algae to feed fish and insects that can also be eaten by our astronauts. The algae will be grown inside a bioreactor, which uses artificial light. It also uses an automatic harvesting and drying system for easier production. Thank you. And now I'll give it to Emilia.
Thanks. So, our mission requires large amount of water, about 330 tons, to be extracted for purposes such as radiation shielding of the habitat, methane and oxygen production, and food production. The most efficient method of extracting water from Martian regolith is by using microwaves, because they heat up and evaporate the water without wasting the energy for heating up the regolith itself. This will be done by autonomous rovers equipped with microwave generators. And after being evaporated, the water vapor will be collected using a funnel and then transported directly, directly to the base via flexible pipes. We calculate that single rover can collect up to 1 ton of water per day, thanks to abundance of water-rich regolith at our landing site. The rovers will be powered directly from the base's solar panels, and we also take into account additional rovers for redundancy. Now let's move to our base camp. So the habitat will have the shape of a flattened hemisphere with diameter of around 16 meters. It will be made out of Nextel Kevlar fabric, the same that is used in Bigelow Aerospace inflatable ISS module. The habitat is designed to be unfolded upon arrival autonomously, and then it will be filled with locally produced water and gases. To withstand extreme Martian conditions, the base will be composed out of layers that each will have a unique task and type of filling. So the outer layer will contain pressurized CO2, which will shape the habitat and provide the rigidity. Below that sits a layer of silica aerogel for thermal insulation. This filling of that layer will be taken from Earth. Below aerogel, there will be a layer of water for radiation shielding, and it will reduce upcoming radiation to below Earth levels. And in addition, it will be also a great water storage. The habitat will have a total of 200 meters squares of floor space, half of which will be taken by the laboratory. If needed, the lab can be extended due to well-throughout space management. And movable interior provides an opportunity to rearrange the interior of the base according to the needs of the moment. Our base have some other features like recycled furniture or edible packaging, but we don't have so much time to talk about that. And last but not least, the habitat will also contain external storage units for resources produced in situ, and also the solar panels as an extra power supply. Now, Antoni will talk more about our vehicles.
Thanks. All right, so vehicles. In order to maximize the amount of science that we can get from the mission, we need to explore as large of an area as possible, and this is where vehicles come into play. Firstly, our rovers. The rover has 2,000 kilometers of range. It cruises at about 25 kilometers per hour, and it has the ability to climb steep slopes of up to 30 degrees. It is able to support 3 astronauts for up to 14 souls. It will be powered by high-efficiency solar panels in combination with methane oxygen fuel cells mentioned earlier. And those big wheels that you can see here in the drawing, those have a diameter of 3 meters, and they are inflatable. This allows the rover to traverse over rough terrain with ease. And apart from a crewed one, we will be taking 2 of the cargo variant of the rover. The cargo variant has an unpressurized interior, and it also has no life support systems, and it is able to carry up to 2 tons of cargo. Next type of vehicle, aeroplanes. So our aeroplane design is based on the RMMP1 concept by Dr. Daniel Raymer. You're probably not familiar with this concept. So it's basically like in the drawing. It's a small cabin hung under a 100-meter long wing. It has 4 electric propellers, and it uses rocket engines for vertical takeoff and landing. And now we have modified the design to be about 30% smaller, and it will have bigger propellers. This will allow us to use less propellant for vertical takeoff and landing. The propellers will use fuel cells, methane oxygen fuel cells for power generation, and also the rocket engines also will use methane and oxygen. We will have a better landing gear system, which will allow us to land the aeroplane in steep and rough terrain, opposed to the original, which could only land on flat ground. The aeroplane has 4,000 kilometers of range. It cruises at 300 kilometers per hour, and it also is able to take half a ton of payload. It is designed to carry cargo, but in case of emergencies, crew can be also transported in their EVA suits. And we will be taking 2 of these aircraft. Before the astronauts arrive, we will also be using them as scout airplanes to better know the terrain. So now EVA suits and exoskeletons. The main focus of our EVA suit design is to allow for great mobility. This is why we will be using mechanical counterpressure suits. If you don't know, a mechanical counterpressure suit consists of a skin-tight fabric, which exerts pressure on your skin, just as regular air would do. But since you're not using air, your joints become much more flexible, hence the increased mobility. Now, these suits will have suit ports at the back, that is ingress and egress hatches, and this will help with minimizing the dust exposure. And now exoskeletons. Since we have only 6 crew members, we needed to come up with a solution to utilize those limited human resources as efficiently as possible. And our answer to that problem is multi-purpose exoskeletons. Firstly, these exoskeletons could be worn by an astronaut, which would enhance his strength and speed. The second use is they could be controlled remotely by an astronaut wearing a VR headset. And lastly, they could operate autonomously, which would help construct the base camp. Weight estimates, here's the weight breakdown. The total mass of all the equipment and people needed to be brought from Earth is 25.6 tons. In addition to that, we will be producing 140 tons of methane oxygen propellant and 340 tons of water. So now a bit about cost. So we can't give you an exact cost estimate other than a couple $2 billion. But instead, we have focused on offsetting the cost by gaining money. Firstly, many of the technologies that our mission will use also have many uses on Earth. Examples include flexible and efficient solar panels, nutrient powder produced from genetically modified algae, exoskeletons, fuel cells for aircraft, and so on. And marketing these innovations on Earth could end up even creating a net profit before the mission even leaves our planet. And secondly, when the mission ends and astronauts leave, they will leave behind lots of valuable equipment on the surface of Mars, equipment that can produce and store hundreds of tons of consumables such as water and propellant. And these hundreds of tons of cargo would have otherwise had to be sent from Earth, and we can produce them on Mars essentially for free. So we could sell those resources to other space agencies to provide an easy start for their own Mars missions. Now, a bit about the strengths of our mission design. Firstly, we have a massive amount of science. We're doing a lot of research in many fields of science in Valles Marineris, which is one of the most scientifically interesting locations on Mars. And we didn't have time to mention all of the activities that we will do. But if you're interested, you can read our full report on that. So safety and risk reduction, there's a couple of things under this term. Firstly, all of our resources will be produced upfront. This means that we will send the astronauts only when all resources have been produced and everything is working correctly. Secondly, redundancy. We're bringing backup copies of pretty much every single piece of equipment. And some of that equipment will be modular and interchangeable, such as fuel cells and batteries. This will allow us to swap out these parts easily. We will be bringing spare parts with us, and more importantly, duct tape. So we also have the ability to 3D print some parts from locally produced polymers. And lastly, about the safety, radiation protection. So our habitat, as Emilia mentioned, has a thick water layer. This will reduce the incoming radiation inside the habitat to below Earth levels. And the astronauts will be spending most of their time in the habitat, about 2/3 of their time. Low mass and cost. I talked about cost earlier, and about mass. All of our equipment could be sent on Falcon Heavy, which would cost about $300 million, not even considering future launch vehicles. And lastly, we're not using nuclear power. So our mission could be executed by a non-governmental organization, such as a private company. And at the end, I would like to thank the Spaceship Foundation, a small Polish foundation that conducts educational programs about space, Nauka to Lubię Foundation, which promotes knowledge about space. I would also like to thank the Mars Society for giving us such an awesome opportunity to participate in such a wonderful event. And lastly, special thanks to all of you for coming here and sharing your time with us. Thank you very much. Okay, so now we have time for some questions. Does anybody have any questions? Well, it depends if we had the same requirements. We would really like to take more people with us on the mission because we have figured out that when you take twice as many people, the mission weight doesn't go up by a factor or 2. So it is non-linear. We could maybe take 20 people and still fit in the 30-ton limit, maybe.
So in my opinion, if we can change something, we should focus on details because in my opinion, our science and engineering and human factors and even costs parts were really good, but we fail on some details. So that's my opinion.
I think it would be better if we had more time, of course, to create the presentations. But overall, I'm quite happy with all the teamwork that we had with these amazing people. We're all very smart. And here, you want to say something?
I don't know. I think we have some mistakes in our report. I think we can change them and do it more correctly. But I think there is no perfect mission. All of missions have some has some weak points because it is impossible to do it perfectly. I'm happy with our report as well, and I also want to thank all of you and my mates and the audience. So I think that's all.
Yeah, go ahead. Yeah, so 3D printed spare parts would be for example, you can't 3D print metal parts from plastic. So bearings and stuff like that, or very complex pieces of equipment, or very pieces that are very likely to break and would be taken from Earth. And 3D printing would be used like for parts that are more easily replaceable. So maybe a part of the rover fuselage or support structure or something simpler. There was another question there somewhere. I'm not sure I understand the question. I would definitely I would, but also I know all the weak points, so yeah, but I still would. I still would.
Also, this whole experience has been so educational and has unlocked so many new features in our just educational life that if we would do it professionally, it would even bring more into our lives, which would be extremely helpful. Also, if we would be paid, be even better, of course.
Thank you very much also.
Are you now or are you later?
No, I'm here to make sure Zoom goes.
Oh, yeah, because their slides weren't moving on the video.
Okay.
It was stuck on the main page. Are you guys already loaded in? Yeah, okay. So you got it?
Yeah, I got it.
Okay.
Which one are you guys? Which, right here? You're done.
Hi, I'm Kian, and this is Shreya, and this is the Ares 1 student design mission to Mars. Okay, so to start off, here are the roles of our astronauts. Mars Not 1 is the commander and will also be a pilot and aerospace engineer. Mars Not 2 will be an astrobiologist and geologist. Mars Not 3 will be a nuclear engineer and will also serve as this mission's general mechanic. And Mars Not 4 will be a botanist and systems operation expert. So besides their main roles, all of the crew members will be trained in first aid. This will help to ensure that if anything happens, there's always somebody able to take care of another crew member's injuries, which is better than having a doctor, because if the doctor gets hurt, then who is going to help the doctor? So all the crew members will be prepared to handle medical emergencies, but in the event something happens that they're unable to take care of, we can handle any of that with telemedicine and contacting experts back on Earth. So the crew schedules will also be predetermined by the mission planners on Earth, with slight control being given to the crew members themselves to be able to make minor adjustments. And if anything serious happens, any emergencies happen, the crew will be trusted to be able to handle it. The crew will also be operating in shifts, which will help to ensure that somebody is always awake and available to take care of anything. And we will also allocate 1.5 day long weekends in order to boost morale. And this is the beginning of science. So for our landing site, we chose Utopia Planitia, and we chose this landing site because it has very large ice deposits, and our mission relies heavily on the use of Martian water ice. It also has relatively flat terrain, which will allow for easy and safe landing. It also has a rich history of mud volcanism, so that would be interesting to study. And it's close to a couple of other points of interest, such as Jezero Crater, which is only around 1,000 miles away, which sounds like a lot, but our long-range rover will be able to transport crew there within a couple of days. So for our main objective, we wanted to study the effects of Mars on humans. This is important because this data is one of the only things that can't be gathered by an unmanned mission to Mars. And we need to understand how Mars affects humans in order to know what to do better on future missions to Mars, and also to help our astronauts maintain peak health. So a couple of the ways that we'll be able to study the effect of Mars on humans is to study the effects of Martian gravity on humans, study the psychological effects of long-term space exploration, and also study the effectiveness of exercise on Mars and neuroelectrical muscle stimulation at preventing muscle atrophy. We can also study the occurrence of blood clots in case, any of our astronauts get injured or cut themselves on Mars. We'll also be studying the effectiveness of Martian-grown crops at sustaining humans, because it's going to be one of our main food sources. And also the effect of the Martian calendar on circadian rhythm, and also future use of medical tech to overcome the Martian environment. So we have side objectives in a lot of other fields. So to start off with astrobiology, we'll be using an ALF device or agnostic life finder to test Martian water and possibly find signs of life, and possibly do long distance EVAs to study hydrothermal vents. We'll also be doing some meteorology objectives, such as dust storm analysis, Mars environmental dynamics analysis, and studies using radiosondes, drop zones, and cameras. So we also have some geology objectives, such as stratum data collection to study the geological history of Mars, observation of glacial patterns, gathering information about the Martian climate history, analysis of ice layers, observation of mud volcanoes, possibly doing a long distance EVA to study lava tunnels, measure the internal temperature of Mars, and measure the seismic activity of Mars. And some planetary studies objectives include studying how the movement of Martian moons affects and investigating methane spikes that are shown to appear on Mars. For our agriculture and life support experiments, we will be testing the effectiveness of Martian soil to grow crops, studying and doing research on GMOs to help improve crop growth in the future, testing out different aeroponic growth methods in our greenhouse, and also doing experiments on grow lights versus the natural Martian sunlight. And for cost, it's kind of hard to get an exact estimate of our cost, but we figured somewhere around the area of $255 billion, with 150 billion being for research and development, 12.7 billion being for structures and vehicles, 1.9 billion being for aeroponic towers and farming equipment, 8.3 billion being for spacesuits, 27 billion being for life support systems, 42 billion being for scientific equipment, and 13 billion for tools and miscellaneous equipment. But all of these prices are subject to change by the 2030s. They could be higher or lower depending on the technologies that are actually developed by then. And so I'll pass this off to Shreya for engineering.
All right. Hi, my name is Shreya Sawant. I'm from Denmark High School, and I'm excited to be here at the convention today. I'll be presenting the engineering section. Okay, so our engineering objectives are to see what technologies don't work as expected, succeed, and what can be improved on. We also test experimental technologies that can be used or expanded upon in future missions. So our habitat is a 2-story inflatable structure based on the Sierra Space Life habitat. It consists of multiple layers of various fabrics that insulate heat, prevent leakage, and protect against outside conditions. Within this fabric is a collapsible aluminum alloy framework that uses lockable joints that unfold and snap into place during inflation to create a strong and rigid structure. This allows for easy deployment with minimal manual labor. Here's a basic diagram of our habitat. As you can see, the first floor is the laboratory, while the second floor is the living space, while the greenhouse is attached to the habitat on the first floor, right over here. So, reducing Martian regolith. Now, a problem that the Apollo astronauts faced was lunar regolith. It was electrostatically charged, which made it very clingy to surfaces. So this made it very hard to brush out spacesuits, and this dust also irritated their eyes and nose, and even in one astronaut caused an allergic reaction. Now, similarly, Martian regolith is also electrostatically charged, so a buildup of this dust inside the HAB can damage equipment and also hurt the astronauts' health. So some of the technologies that since been developed to combat lunar dust can also be used for Martian missions. One of these include an electrodynamic dust shield on the outer layer of the EVA suit, which is a pattern of electrodes that generate an uneven electric field which levitate the dust off the suit. We also have an indium tin oxide coating applied to windows and the visors. This dissipates buildups of electric charge, therefore reducing the dust. We also have electrostatic precipitators that filter dust from the habitat air circulation. Now I'll be going over the 4-seater pressurized vehicle. Our 4-seater pressurized vehicle is made for use for long distance travels. Some of the main features of this vehicle are the Nitinol dash spring tires, which, as seen in the picture off the side, can mold around obstacles, therefore reducing damage. This type of wheels have been successfully demonstrated in simulations of lunar and Martian terrain. This vehicle also has EVA capabilities, storage space for samples and water, a cabin for the crew, a ground penetrating water radar, and a Mars environmental dynamic analyzer to study the weather. Here's a basic diagram of our 4-seater vehicle. Our 2-seater vehicle is mainly used for short distance travel. It also has a ground penetrating water radar and its spring tires. For navigation, our crew will use the HiRISE camera on the Mars Reconnaissance Orbiter. This camera is powerful enough to capture pictures of rovers from space. The data from this camera is going to be used to map routes to important locations, such as scientifically interesting sites and water deposits that the crew will regularly return to collect their water. We also use the vehicle's inertial measurements, such as gyroscopes and odometers, to help better track our routes. energy source. We have selected energy source to be a reliable power source for this mission. We didn't choose solar power for 3 main reasons. One, we receive limited sunlight during limited times, such as during the day or in clear weather. 2, dust in inclement weather, such as dust storms. And 3, the amount of panel surface area needed to provide enough energy for the mission is inconvenient, as it will be a heavy payload. On the other hand, we used the Krusty reactor, as one 10 kilowatt Krusty reactor would stand at 11 feet tall and weigh only 4,400 pounds. This design gives it a very low likelihood of posing a nuclear threat. On this mission, 2 10 kilowatt reactors are used to power this mission. Optical laser communication. The habitat will communicate with Earth using an optical laser communication system based on the recently launched LCRD payload. Past missions have mainly used radio wave communications, which have a very limited data rate. While on the other hand, optical communications have a bandwidth 10 to 100 times more stronger than radio wave systems, while the payload for the system being smaller, lighter, and less power consuming. With optical communications, a map of Mars that will take 9 weeks to send can be shortened to 9 days. This allows for better coordination with researchers who study the data that the astronauts send. Ground penetrating water radar. As our landing site, Utopia Planitia, as detected by the shared instrument on the Mars Reconnaissance Orbiter, has large subsurface ice water deposits at least 10 meters below the ground. A ground penetrating water radar based off the Perseverance rover's RIMFAX instrument currently has at least 10-meter range. This radar will help detect ice and water deposits. Drills. We have a drill rig present on the 4-seater vehicle and a 2-seater vehicle. So we use 2 main drills on this mission: the mechanical drill, which can drill as low as 10 meters deep to collect samples or to reach ice water deposits, and the hot water drill, which is used after a mechanical drill has cleared a hole to the surface of the deposit. This hot water drill melts the ice and deposit, creating a cavity of water. Rod wells. After our hot water drill has melted and enough ice, the rod well is installed. This rod well is a pump submerged into a cavity of melted ice that cycles heated water to stop the water from refreezing and to melt more ice in a deposit. This water is pumped up to the surface to either be reheated or transferred to a water storage tank. The 4-seater vehicle has this water storage tank. Once it is filled, the water can be brought back to the habitat for analysis by the ALF device and for further processing. In situ resource utilization for oxygen. A briny water electrolyzer will be used to separate our water into hydrogen and oxygen. A device developed by Washington University engineers, simulated under Mars-like conditions and using the same amount of input power, was capable of producing more than 25 times the amount of oxygen than the MOXIE experiment on Perseverance. As our Earth's atmosphere is made of 80% hydrogen and 20% oxygen, we'll include a supply of imported nitrogen to maintain this Earth-like breeding mixture. Trace gases, like any byproducts of human metabolism, are collected using activated charcoal filters. The Sabatier process. Additional water can be created using the Sabatier process. Hydrogen is available as a byproduct of the briny water electrolyzer, while carbon dioxide can come from exhalations of the crew. This in turn produces the water we need and methane. Now, methane can be used as a potential rocket fuel in future missions, as methane is more stable and be stored at more practical temperatures than the commonly used liquid hydrogen. Methane is also denser than liquid hydrogen, therefore, and requires less insulation. Therefore, smaller and more economical fuel storage tanks. Companies such as SpaceX have already begun using methane fuel. Passive radiation shielding. Unfortunately, Mars does not possess a magnetosphere like Earth. So the 2 main types of radiation that astronauts will face are GCRs, which are high energy particles that speed around space, which constantly bombard Earth and Mars. We also have solar proton events, or solar particle events, in which particles near the sun are launched out to space during a solar flare. Although these are short-term events, they'll expose the crew to elevated amounts of ionizing radiation. During solar proton events, all activities outside the habitat will be canceled until deemed safe. Passive radiation shielding continued. Some of the materials that we use for passive radiation shielding include HDPE, Kevlar, hydrogen-loaded boron nanotubes. And we also considered another material, lithium hydride. Unfortunately, it was not chosen to be used on this mission because of its powdery texture, hazards to human health, and high reactivity to water and oxygen. Spacesuit. So our spacesuit uses a combination of the mechanical counterpressure suit design and a gas suit design. Our IVA suit, or intravehicular activity suit, uses an adjustable mechanical counterpressure suit based on the MIT biosuit, while our EVA suit is a partially gas pressurized suit, which provides protection from outside conditions and a life support system. Some of the human-machine interface technologies seen in the NASA Hot and Mars project is the Collins Aerospace ITIS, an AR display in the visor that provides EVA statistics, maps, notes, checklists, and other statistics. We also use the Intention Astronaut Smart Glove, which uses gesture technology to control robots. A small drone brought on this mission can be controlled using this astronaut smart glove. This drone can provide a high-resolution image of Mars from above. Solar Montgolfier weather balloons. As one of our science objectives for this mission was to study Mars's meteorology, we'll be periodically releasing solar Montgolfier weather balloons. Some of the instruments we include on these weather balloons include radiosondes, which measure atmospheric variables such as temperature, pressure, and wind direction. We also include cameras, which provide visual data of the balloon's journey, and dropsondes, which we attempted to be deployed over dust storms to study this planetary phenomenon. We have one main engineering demo in this mission. We're going to test the ability to create a localized magnetic field from a superconductor. Superconductors are lightweight but powerful materials capable of making a magnetic field stronger than the ones made by conventional magnetic materials. Some of these high temperature superconductors can operate in the same temperature range as Mars's. To determine the efficiency of the superconductor, the astronauts will test the dose of radiation inside the magnetic field and compare it to the current surface radiation levels and the efficiency of passive radiation shielding materials. I'll pass this on to Kia.
Okay, so for life support and human factors, there are several things. One of the most important is water and water processing. So 360 gallons of water will be imported from Earth to sustain the crew for the first few months of the mission. We think that this will give the crew enough time to set up their ISRU water collection system, which will be used for the rest of the mission. We also assume that by the 2030s, a 96% effective water recovery system will be developed, which will be improved from the ECLSS, or Environmental Control and Life Support System, used on the ISS. So our system will both recover water and recover air breathed out by the astronauts. We'll also be using Argonide's nanoceram filter to remove biological contaminants and small particles within the water processing system. And one important thing to note is that Mars water contains perchlorates, which are toxic to humans in large doses. So we'll be using a catalyst inspired by anaerobic microbes that removes more than 99.9% of perchlorates from the water. So for food, we chose an aeroponic greenhouse system. We chose this because it uses minimal water compared to hydroponics and traditional farming. And aeroponically grown crops also have significantly higher yields and shorter crop cycles than other growing methods. Alongside our greenhouse, 2,000 pounds of food will also be imported from Earth, which we think will last the astronauts around 4 months. This gives sufficient time for the crew to set up the greenhouse, and any remaining food will be reserved for both the emergency supply and also just for extra food that can be added to meals to avoid menu fatigue. And waste management is also very important. So the mission's trash, while we will try to recycle most of it, we will be taking any trash that is left over and that can't be recycled and putting it back onto the ascent vehicle to be transported back to Earth, as to not contaminate the Martian environment. And I'll do this one too. Radiation protection medicine will be used. And so astronauts will be exposed to a lot of radiation in their journey in space and also on Mars. There are several passive radiation shielding methods that we're using in this mission, but we will also be using a medicine that can be used to treat high doses of radiation and minimize the effects of radiation sickness. And then I'll pass this back over to Shreya.
Thank you. Now, the physiological and psychological effects of space on a human body was a major factor in determining the length of this mission. We wanted to give enough time for the astronauts to conduct enough research, but also take into consideration how the 2 years and 2 months they'll spend on this mission will be the longest that any human has ever spent in space, as per the current record of 437 days. Now, this extended period of time in space will definitely lead to bone and density loss. To combat this, the astronauts will do 1 to 2 hours exercise daily using the bicycle, treadmill, and an advanced resistive exercise device. In any case, the astronauts are somehow incapable of doing exercise. The neuromuscular electrostimulation device serves as a temporary alternative. This device sends electrical impulses to the nervous system, causing muscles to contract. This device is used in bedridden patients to offset atrophy. This, combined with the healthy diet and adequate rest, will keep the astronaut's body strong. The habitat's medical bay can also be used to treat and quarantine sick or injured crewmates. Psychological health. The long-term isolation from Earth, stress from workload, and extended period of time in cramped quarters with other crewmates are all factors that can harm the astronaut's mental health and cause division among the crew. Monthly evaluations will help to document an astronaut's well-being throughout this mission. We also recommend journaling thoughts on a regular basis, as it be beneficial to reducing stress. Each astronaut is also allowed to bring 12 pounds of personal belongings and a selection of ebooks, video games, movies, and etc. The information gained about space's effect on the human body on this mission will help us understand how to better extend how long an astronaut can stay in space, with the goal of a permanent settlement of Mars, and answer important questions that allow us to advance humanity into a multiplanetary species. Acknowledgements. Thank you to the Mars Society for providing us this opportunity to present, our mentor Hertina Mogosanu for advising us, and the audience for listening to our presentation. Questions, comments, concerns? Okay. Yeah, we were planning on just disposing that extra port. That's very interesting. We'll look into it. Any other questions?
I think definitely just having multiple backup plans set into place, because there's a lot of, we ran into a couple of big bumps during our the whole process of putting together a presentation and doing all the research. And I think just everybody having a backup plan in case, you know, something wasn't received in time, or there wasn't enough communication between the team members. I think it just would have been nice if everybody also devised like a little plan that we can all combine together to replace parts that we might not have necessarily received on time. For me personally, the thing that I'm most passionate about is a lot of the power source information. I'm really big into researching things on like different clean energy sources, alternative power like nuclear, and obviously there's other alternatives for clean power. But that's what I'm personally the most passionate about in this specific presentation. How about you?
I think I was really passionate about the idea of how to create a permanent settlement. Now, our mission design was based to be the first manned mission on Mars. So our objective of humans, like studying human the study of the human body during our space travel was a major objective, as this information will allow us to establish a permanent settlement. So I was really interested in seeing how we could have support the human body in space. Yeah. Awesome.
Thank you, remote attendees.
Mars Society host for this. This is Greg Kennedy. I think we are ready to rock. If you give me the okay.